Thanks for having me. So you said I'm Jeff Heer. I'm a professor at the University of Washington in Seattle, back in the United States, but I'm here on sabbatical, really enjoying a year here in Berlin. And so the title of these slides is Agency and Automation, which are themes I've been thinking a lot about in recent years and really infused some of our research projects. I was also prompted to think about ethics and discuss that with you tonight, so that will be an organizing frame as well. So for example, in data visualization, it's not at all uncommon. In fact, I'd say perhaps one of the most common conversations around ethics is what I would call representational ethics. So for example, how are people being represented in data and design? And is those helpful or harmful in terms of what they perpetuate and communicate in society at large? So one example that many of you I'm sure are familiar with that's been held up as one of the more thoughtful examples of showing people is this work by Periscopic showing gun deaths in the United States. So in this case, it's conceptualized as the arc of a life being cut short by gun violence. And so, for example, in this case, you see the trajectory of a person and then it drops. And then shows like basically what their life might have been corresponding to demographic models. And it starts with some point examples to show that these are real people, and then escalates to show just the massive scale of lives lost, not just the lives, but also the years of experience lost alongside that. And this could be kind of contrasted to other examples, which I'd say are not so thoughtful, but I haven't shown those there basically in respect for the people who may have been making honest and legitimate mistakes. At the same time, there's many other issues in representation. For example, Berlin's own Lisa Rost had a nice blog post about a year ago analyzing the use of colors to represent gender across a number of different newsrooms. So these are examples showing traditional blue-red polarity to try and communicate males and females, which you'll often see in graphics such as population pyramids. And then goes on to discuss both the fact that these are familiar, so there's some advantages to that, but they also uphold long-standing stereotypes, and so they may be harmful as well. And canvas, for example, different alternative palettes that designers have explored for trying to convey nebulous concepts such as gender. These examples are both ones where I think the decisions are right there in the designer's hands, and so we have maybe sometimes difficult decisions on how to go, but they're right there, kind of under our control. As we move into more data-rich environments, that gets harder, and that we'll be building models and services that are infused by data collected from any number of sources that we may not have control over, and may also have biases that we're unaware of. So just some examples in the space, these titles from an article that ran in The Guardian, and was dealing with issues of data-driven services. Some of you may have seen things like Microsoft's Take, which was a chatbot that was released onto Twitter, but also evolved. So it was retraining and tuning based on the conversations it had with people. And so people adversarially really tried to change the model behavior, and they succeeded, taking Tay from humans are super cool to full Nazi in less than 24 hours. Right, so this question's about deployment of data-driven services and the degree to which they're going to interact with the environment and the rate at which you update models and what kind of quality control procedures will you put in place. I'm sure many of you are also familiar with the case of Google releasing image classification software which was producing biased and dehumanizing results. And so this raises an onus for us as product managers, as designers, et cetera, in terms of how do we understand these problems, many of which may be unintentional or latent in these services before we release them? And that's an open question and one active area of research. Just one example, this is a system that was done by my student at UW, Yang Liu, where we're trying to visualize the high-dimensional spaces that are called latent space representations that are learned by machine learning techniques. So in this particular image, the underlying data set is what are called word vectors. So you basically take a large corpus of text and from that try and learn representation of words as points in a high-dimensional space where the similarity of those points in that space should have both syntactic and semantic regularities associated with it. At the same time, we can actually learn unintentionally, as it may be, the biases implicit in these data sets. So what this visualization is showing you is that a couple of data points have been manually selected that are definitionally gendered. So things like man, woman, father, mother, son, daughter, etc. We take all of the points that are associated with male terms and those with traditional female terms, take their center points and use that to define a vector. And that's the x-axis you're seeing here, which is in this large vector space, here's that one line that's kind of between men and women ideas as reflected by those terms. The y-axis is then using a form of multi-dimensional projection that's trying to show the global variance in the rest of the data. And doing this, we can uncover some things that are a bit concerning. So for example, if I draw out this bounding region here, so selecting points that are within this region defined by the definitionally female terms, we get, for example, the set of selected words on the left, revealing common gender stereotypes that we might not want to have underlying the various types of service, including autocomplete for emails, natural language generation and classification, that's really paying service to ideas that may not be what the values that we want our systems to reflect. But I'd argue there's something that at least I find even more concerning, which is notice where the bulk of the points are. The mass of this data shifted towards the left, basically more definitionally male. And so if you look at the texts that undergird this particular model, I wouldn't be surprised to find that they predominantly feature men as the main actors and doers of things, and therefore associated more closely with a wide variety of terms that you or I might traditionally consider quite gender neutral. So the ability to be able to visualize and inspect these models, and I think really we're still at the beginning of forming better quality control mechanisms, is a really important task both for researchers and practitioners today. So again, these are examples of what I call representational bias. I'd say another common topic in visualization is what we might call inferential bias, which is when we create a visualization and other types of data tool, how does it bias or lead people to certain decisions versus others? And are those accurate or robust or reliable decisions? Often this has to do with how different people interpret visualizations. This is where it ties into visual and data literacy as well. So one of my favorite examples of this is actually in hurricane forecasting. So many of you have no doubt seen graphics like this before, where you have this cone of uncertainty, which is actually a confidence interval given a number of different simulations, trying to predict where the center of the hurricane will be at any given time. Given the use of certain visual encodings, though, this might be easily misinterpreted as, for example, is it the size of the hurricane? Is it the severity of the hurricane? There's also issues that might arise due to a lack of statistical literacy, which is quite understandable in cases like these. So for example, looking at this graphic, I would conclude that the shore of Texas is completely safe, whereas the Gulf Coast states of Mississippi and Alabama are the ones that need to be concerned. And statistically, this is the case. However, there's still a non-zero probability of other events happening. And so a lot of recent research and visualization has been looking at other ways to communicate uncertainty. And one common approach that's proven effective in many cases is one of frequency framing. So that is, instead of trying to show an aggregate or model result of the uncertainty, you actually make the certainty more perceptually apparent by showing individual instances, but ones that are represented. So in this case, we're trying to use a representative sample to make sure we're actually capturing some of the more rare events, but in proportion to their actual predicted occurrence. So doing that, we get very similar information to what we saw to that cone, but we also see that it's possible, though unlikely, that hurricanes might drift into Texas or other states like that. And this might be a more useful way of communicating to the public, particularly when they're going to be making decisions and how do they respond, for example, when a call for evacuation is made by the local or federal government. Now, this is an example of inferential bias that these different visualizations might have, but I'd say with a rather complex topic and a visualization. But these types of issues can also emerge with much more mundane, everyday, or simple visualizations. And to illustrate this, I'd like to run a quick experiment here. Hopefully we have just large enough a sample size to get some interesting results in the room. So the experiment is as follows. I will show you two shapes, and your job is simple. You just have to judge how much larger the big shape is than the smaller. And don't cheat by using your thumb or finger or other measuring device. Just make a quick visual estimate. Don't yell out the answer. We'll take a poll together. So first up, circular area. So how many times larger is the big circle than the small circle? So go ahead and take a look. Make your estimate. And now let's see. How many people think the big circle is 4 times bigger? Okay, some of you, great. 5. All right, some of you, 6. Right, some people, 7. Another number of people, 8. Okay, got one, 9. Okay, all right, a number of people, 10 or higher. Okay, so why can't you agree? That's a pretty big difference. You go from a scale factor of 4 to a scale factor of 10 or higher. Check your eyes. Like what's going on? Let's try again. This time with the length, in this case also area of bars. How many times larger is the big bar than the small bar? So let's go ahead. How many people think the big bar is 4 times bigger? No one. 5? No one. 6? A couple people, all right. 7? A lot of people, all right. 8? A lot of people again. 9? No one. 10 or higher? No one. So nothing else. Notice that the distribution here was much tighter, right? In this case, around 6, 7, 8, with no one on these long tails of 4 or 10. And as you may have guessed, the answer is the same in both cases. It's 7. So in this case, you get there. I think you said 8. That was very close. Within the margin of error. Don't worry. And you can maybe melt these balls down. They would be an exact match in terms of the area versus in the case of the bar to Heer. And for example, in the area of psychophysics, all the way back to like the 1950s onward, people have been studying this. Now we actually know that there are nonlinear responses to various types of perceptual stimuli, whereas things like position and length tend to have a more or less linear, that's a 1-to-1 response in expectation, whereas other things, including area, even worse volume, even worse brightness, are subject to types of perceptual distortions. It's just kind of how our perceptual system works. So we can run experiments like this for various types of decoding tasks. The one we just did was one of comparing proportions, making a proportional judgment. And then we can try and analyze people's time to response. We can analyze their error and use it to try and provide some guidance in terms of what types of visual encodings might lead to more quicker and more accurate understanding of data. This was done originally back in the 1980s by statisticians and psychologists. This particular chart is a replication of these results done by my students and I using platforms like Amazon's Mechanical Turk to reach larger pools of participants. And it's for reasons like these that you often in visualization textbooks see diagrams often giving a hierarchy of different visual encodings for different tasks. Again, this is specifically for the task of comparing proportions, and you might arrive at different rankings, and in fact you do if you look at different tasks such as, are two things the same or not? Like, do they belong to the same category? Or are they rank ordered? And again, this is just for comparing two values. When you go to looking at aggregates, other concerns come to the fore, as we saw with the hurricane visualizations. So part of what we do in visualization is try and study this stuff to get a sense of what are the different inferential biases different visual forms might bring. And then in my own work, then try and figure how will this impact how we develop tools. But there's a bit of a tool maker's dilemma in that, we build a tool, you're trying to help people do things effectively in the world, but you're also operating at a bit of a distance, right? So I can't control necessarily what people do with the various tools I develop, but there may be ethical implications both for what they do with those tools, but also how the tools themselves might nudge people in certain directions, one way versus the other. So for example, over the years, my collaborators and I have built a variety of visualization tools. For example, my former student, Mike Bostock, led our work on the D3 project. And a number of students, recent grads from University of Washington and I built systems like Vega and Vega Lite. Oftentimes we're guided by multiple ethical concerns. One is, of course, we're trying to build tools that are useful, that allow people to create valuable visualizations, ideally with a high expressive ceiling, like there's a variety of designs they should be able to create. At the same time, we also put a lot of thought into what is the path of least resistance. So that is, if you kind of use the tools in these sort of least effort ways, where do you end up? And are those more beneficial than like some of them maybe more problematic visualizations? Do those come about through more effort, or are they easy? We can't control that perfectly, but it's certainly something that we've thought a lot about and discussed as we've made different design decisions over the years. But more recently, I've been thinking about taking that to the next level, like what happens when our tools become more opinionated, which I think gives rise to a dilemma in ways that can be both helpful and perhaps hurtful. So how might our tools help us to become better analysts? So one is like, do they have whether it's through path of least resistance or through active suggestion, so they take advantage of some of the ideas I've discussed earlier in terms of biasing towards visualizations, for instance, that might be more easy for a large body of people to interpret. We might also take it further and think about the process of data exploration and analysis that people engage in. So for example, in my teaching data science and visualization courses, I often see a number of pitfalls that at least novice analysts tend to fall into. One is almost completely overlooking data quality issues, not realizing that serious issues in the collection and representation of the data actually undermine any sort of implications they try to draw. In other cases, I've seen many examples of students fixating on specific hypotheses they had, building models and visualizations specific just to those, and overlooking confounding, perhaps causal or explanatory factors that are actually relevant to the analysis at hand. And these are just some examples. There's no shortage of biases that you might find. Cited here is a famous paper in 1999 about biases in intelligence analysis. And for the popular press, some of you may have seen Danny Kahneman's book, Thinking Fast and Slow, which is sort of a popular treatment of a lot of the original cognitive bias work. So this led us to think, well, can we build tools that, again, are more opinionated and hopefully nudge us, in a more effective direction, as opposed to just having blinder vision, for instance, and overlooking some of these important issues. So our first baby step in this direction was the work of my former student, Kanit Wangsapasawat, and other collaborators. We built a tool called Voyager. So let me jump out of the slides and give you a quick demo of this. And the idea is to help nudge people in the process of exploring data. So really it's got visualization for exploratory data analysis. Rather than starting with an empty view, we start with summaries of each column of this data set. And each visualization has been automatically generated and actually guided by some of those perceptual guidelines I discussed earlier. So we can see things, for example, like the number of cylinders in each engine in an automobile. That's what this data set's about. Including perhaps surprising anomalies, like the inclusion of 3 and 5 cylinder engines. We can see that there's not a balance in terms of the different regions from which these cars come. We can see the time period over which they were created. In this case, it's the 70s into the early 80s. Some of you no doubt recognize this as a classic data set used throughout statistics. Then we can go on to see things like different distributions of quantitative values, and get a sense of how they're distributed. Really to give us a sense of the shape and structure of the different variables in this data set and catch potential problems here before we move on to focus on more specific hypotheses. Now these were automatically generated, but it's equally important, of course, to keep the user in control. So if I want to, I can use this completely manually. I can dismiss these, for example, with a hide button. And I can drag and drop things such as, in this case, say I'm interested in mileage. I can drop that on this Y shelf to encode it on the Y axis. Then you note a number of design decisions were made automatically, including the choice of mark as these strips to minimize occlusion or overlap. So again, trying to apply some principles to nudge people in directions of ideally more effective visualizations. But then we get recommendations that are conditioned on this specific focus view. So for example, here's summaries, a histogram of that distribution, as well as the sample average for this data set. As I go down, I can see you're basically expanding the search frontier and an exploration. What are relationships between mileage and other variables? So for example, here's the relationship with acceleration. And I can maybe look for high mileage cars, ones with better fuel efficiency. I'll notice that in this data set, many of them are Volkswagens, presumably from before the cars knew how to lie about their mileage. So I'll trust that. And so on and so forth. In this case, ending at a visualization showing the change in mileage over time, and it seems to be improving. And I might find this interesting, or I might be curious how I can construct this chart. So for instance, if I mouse over these little shelf icons here on the right, notice that the encoding shelves update. So this recommendation is also trying to show me how to create this chart, maybe serving as a form of education to help new users learn how to be richer in their use of the manual operations of this tool. I can also click this to make this the new focus, and then I get corresponding recommendations that then are rooted in this particular focus view. For instance, I can see a summary view that's showing the average over time. Maybe that's less cluttered and closer to what I'm interested in, so I could pivot to make that my new focus. Now I get recommendations that are looking at categorical subdivisions of this data set. So for example, mileage by the number of cylinders in the engine. Unsurprisingly, 8-cylinder engines perform the worst in that case. I can also see subdivision by region. In this, I noticed that cars from the USA seem to be showing significantly worse mileage than cars from other regions. And I might attribute this to any number of cultural factors, but I think it's a little too early to jump to that conclusion. So for example, if I instead make this the focus, I get another set of recommendations. Some involve just the choice of visual encoding. In this case, it's only 3 series, so it's not so bad, but you can imagine as more time series overlap, you might get clutter and it might be difficult to see individual patterns. So one recommendation is to break this into a trellis plot, or what Tufte calls small multiples, to see each trend in isolation. If I want, I can also exert some control over the types of recommendations I'm getting. So for example, showing only categorical fields, and then I see a breakdown, not just by region, but by cylinders. And once I do this, I can see, for example, that the US is the only market here producing 8-cylinder engines, which is actually driving that average down. And if I want a more fair comparison about the mileage from different producing regions, I might look at those conditioned on the same number of cylinders, and it's giving me a more equitable comparison. So again, this is one of those confounding factors that we'd want to take into account if we're thinking about what are regional differences in automobile manufacturing. So that's the demo of the Voyager system, and give you a sense of how that works. So to recap, a key idea here is that when we augment manual exploration with visualization recommendations, and particularly ones that are sensitive to the user's current focus. Our goal here is to support systematic consideration of the data, but hopefully without exacerbating false discovery. That's why we're not doing random correlation mining and various types of statistics across the data and showing visualizations that A, may be spurious in their results, and B, may be distracting from the questions that that specific user has and that they're trying to explore. So really trying to put the user in the driver's seat and provide useful augmentation, not overriding their agency. To do this underneath the hood, we model the user search frontier, as I mentioned, by searching for related chart specifications that are seeded by that focus view. That's really how we're trying to keep it focused, again, on the user's intention. And underneath the hood, we actually generate a number of different chart designs, in this case using the Vega-like language developed in my lab. And then we use a model of design constraints and perceptual effectiveness, really learned from the types of experiments that we did in the room earlier to help drive those recommendations. So we're using both old school 1980s AI techniques, the combinatorial search, but also modern statistical machine learning methods to learn ranking functions from experimental data to provide these kinds of recommendations. But perhaps most interesting is how this fares with real people. So we brought in a number of people with analysis experience and ran user studies comparing Voyager with more traditional user interfaces without recommendations. And we found that our basic goals were met and that people were more systematic in their consideration of the data. So we looked at basically what are unique combinations of variables and whether or not they were seen and interacted with, and both improved in a sense or increased, and that people were looking at a broader swath of the data. More interesting though is having people reflect on their experience. So one quote was that the related view suggestion accelerates exploration a lot. People really found this help them move through the data more quickly and in a more comprehensive fashion. So that's good, right? Notice is a lice that it shows me what fields to include in order to see a specific graph. Otherwise, I have to do a lot of trial and error and can't express what I wanted to see. So this sort of augmentation, with a little bit of automation, seemed to also help learning, and that these recommendations, but also queuing into UI devices that show how to construct that recommendation yourself was in fact something that people valued as a learning device. But my favorite quote, and I think the most interesting, cuts in a slightly different direction. These related views are so good, it's also spoiling. I start thinking less. I'm not sure if that's really a good thing. And this is interesting because as we approach this work, we very intentionally were in opposition to full automation. I'm terrified of a world in which we have these machine learning techniques trying to automate what was formerly the purview of people, in many cases kind of overlooking a lot of the nuance, ethics, and domain knowledge that people bring to a task. We're trying to bring in augmentation in a way that's helpful. But nevertheless, we're seeing perhaps an interesting trade-off here where there's various kinds of productivity benefits, but what does it do in terms of how we think about and approach these tasks? And if we're too good and if we become too complacent, do we just start taking the machine recommendations and start thinking less critically about what we're trying to do? I think that's a major pitfall in design in this area, and one that I think hopefully appropriate designs might usefully mitigate. And it's not just this one point example. I won't talk about these in any great depth, but to a number of areas, we've been looking at projects that are trying to figure out what is an appropriate balance of automation and control. And this depends on many things. It depends on the task. It depends on aspects of, for example, how safety aware or ethically aware we need to be. What is the familiarity and of the user and so forth. So a really difficult design challenge, I think. We've approached it in areas such as data transformation, where we build tools for interactively transforming data for data preparation. That was a research project that we later commercialized as a company, and we have now an office here in Berlin for Trifecta, where I've been working. And part of this is driven as people indicate what they care about in the data set. We make suggestions of potential transformations that might help them get the data ready for downstream visualization and analysis. In a completely different project, we looked at similar user interfaces for language translation. And that how do you combine skilled human translation, but augment it with the results of machine translation engines that in recent years have gotten much better? What's the right balance there as well? And then we saw similar results as in Voyager, in that people created, actually was rated as higher quality translations. And for a variety of translators, we're actually generating more consistent translations, which might be useful if you're hiring a team of translators. But nevertheless, the translators felt it also affected their process. They felt they were less susceptible to being creative, or the machine translation distracts from my own translation process by putting words in my head. And this could be both a good thing and a bad thing, depending on your perspective. I don't think this lends itself to easy answers, but I think rich and very important design challenges, again, at this intersection of data and design. And so with that, I'll just end my talk with some outstanding challenges. I won't talk to all these points, but roughly all of the projects we've looked at are literally someone's PhD thesis. And so the way that we can build tools that allow people to explore and develop these types of interfaces, get designers, not just computer scientists like myself, involved, I think is important. Ways of better mapping and constraining machine learning models, making really informed production and deployment decisions is another important task, again, echoing the beginning of the talk. And then finally, these issues of agency and automation, I think, are incredibly important as we keep releasing more and more forms of machine learning augmented services. We have to ask not just how well does it perform, but what is it doing to us? And which things do we like, which things don't we like, and how do we more effectively design for that in the future? So that's it for me. Thank you very much for your attention. I'm excited to begin.